So we're going to focus on circular economy and bio-based materials. That's an area that's rapidly moving from concept to commercial reality across the industry. In light of the fuels and feedstocks impacts of the current geopolitical events, reclaiming the value of as many of our molecules as possible has never been more important for resiliency. So from rethinking feedstocks and designing for circularity to scaling technologies that reduce waste and emissions, this topic sits right at the center of how we build a more sustainable and competitive future for the chemical industry of manufacturing. Across the value chain, companies are working to turn these ideas into practical, scalable solutions, and that's exactly what we'll explore here today. I'm pleased to be moderating this conversation on behalf of the American Chemistry Council, and we're joined by two industry leaders who are directly involved in advancing these technologies. So Seval Schichtel, from the Global Business Development Manager at Clariant Catalysts, as we heard from Lee, and Kyle Findley, running a business unit called Green Circle that we'll learn more about in Lummus Technologies. So Seval and Kyle, welcome, and maybe give you a chance to introduce yourself a little bit. Seval, I'll start with you. Thanks.
Thank you very much. Good morning, everyone. So yeah, my name is Seval Schichtel. I am working at Clariant since almost 20 years now. I've joined this company in R&D first, and since from background I'm chemical engineer and I've done my PhD in catalysis, so it was a great opportunity to start with my career. And after several functions and roles in R&D, I then moved to the commercial side of the business, to the business development and sales management. And within this team, I took over the responsibility around innovation projects and, for example, plastic recycling. So that's why I'm very happy to be here today and to have the opportunity to discuss this very exciting topic. Yeah, thank you.
Thank you, Seval. Can't wait to dive in a little bit. And Kyle, how about you?
Yeah, thanks, Mitch. First of all, just want to say thank you to Lee and the whole team at Hydrocarbon Processing and Gulf Energy for organizing this event. It's been a great event so far, and I'm sure today will be as well. And it's an honor to be up here with Mitch and Seval today to talk about circularity, and I'm really looking forward to the discussion. So my name is Kyle Findley, and I lead a business unit within Lummus Technology called Green Circle. The purpose of Green Circle is really to develop and commercialize new technologies, particularly in the spaces of circularity and sustainability. What we do is largely we partner with companies that have developed differentiated technologies, typically up to the kind of demonstration scale level, so kind of TRL5, TRL6. Sometimes those are small startup companies, sometimes those are large, well-established companies. What we do is we step in and we help them with that development path from demo scale up through commercialization by providing engineering expertise, scale-up know-how. Sometimes it's just engineering bandwidth, and then ultimately licensing support. So what we do is we provide that assistance to them on their scale-up journey. And then kind of in return, what we get is the right to license the technology to third parties globally. So again, look forward to the discussion today, and thanks.
Fascinating, and I think we're at an exciting point in this technology because the technical readiness is pretty advanced. We're seeing things in production at scale. The business readiness is really what's next, and how do we jump onto the business cycles to find the profitability? I think we heard from the keynote speaker. There's a lot of new potential. There's a demand for and a challenging demand for energy and the other basic inputs as well. So we're going to spend about 45 minutes here, and please do. There's going to be time for questions at the end, and please make sure that you're taking notes if you want to jump in and join the conversation. So let's start off in the questions. Seval, to start off with, can you explain why circularity has become such a critical issue today?
Well, Mitch, to be honest, here the numbers tell along the story, really. As I moved to the business development team 6 years ago, and I took over the responsibility for plastic recycling projects, I found it really exciting to have the opportunity to somehow contribute to this very important topic. But what I was not aware is how much I will learn about the numbers. So, for example, if you look at the current market situation, we globally produce roughly 400 million tons of plastic. Okay, what I was not aware of is what is happening with this material at end of life. Yeah, so for example, the first number I was not aware of and really shocked to hear is, what do you think which proportion of this amount is going to single-use plastic. So that means we produce these highly sophisticated products. I mean, probably most of you here in the room have chemical background, so you know what it takes to produce a polymer, what we call a plastic. It's highly sophisticated materials. So to produce it, use it just one single time and dispose it. It's about a half. The half of this amount is just to be used once, and then it's disposed. Okay, well, that was the first shock. Then the next thing that I've learned is there are very good market reports out there and describing which part is going to be landfilled and incinerated. But that's the largest part, actually. 65% of what we are producing every year is going either to be incinerated or landfilled. Wow. So that means it's not being reused in the same cycle. And I would say the last numbers I want to highlight here and to mention, because it was really, I was not aware about the proportion of this number. We all know these very famous pictures of plastic waste in the seas, in the oceans. Yeah? I must say, sadly, famous. And I was not aware about how much that represents compared to the material that we produce. Is almost 20%, 19%, I think, of a material that we highly sophisticatedly produce is just mismanaged. We call it mismanaged or not managed, simply lost to environment. 20%. I mean, I think these numbers really clearly show the situations. It clearly shows that something has to change. And from a chemical industry point of view, I would say we have the tools to do so. But most importantly, maybe even the responsibility to change this. Yeah.
Well, that's a great observation, and it does frame the issue of this large scale. And we are talking, and it's not a direct correlation, but we are, there's a scarcity problem right now with feedstocks and other things. And as we look at the materials that we jettison and then we don't reuse, the value proposition changes a bit when you think about how that might, coinciding with the development of the technologies, the kind of the increased affordability of those technologies and the potential reuse of these molecules, it comes a long way. But we do have a long way to go. So thanks for framing that for us. Kyle, at Lummus, you have built a platform, Green Circle. Can you tell us a little bit more about that and how you approach this challenge?
Yeah, sure. So, at Lummus, we have a deep fundamental understanding of how to convert virgin hydrocarbon feedstocks into petrochemicals and polymers. We have a portfolio of 160 some odd technologies in the refining and gas processing, petrochemicals and polymer spaces. So about 7 years ago, we established Green Circle. We made a strategic decision to complement our expertise in petrochemicals and polymers production with circular technologies that can integrate back into those petrochemical and polymer linear value chains. Our CEO kind of likes to summarize that strategy in a single line, saying that our ambition is to be involved in the making, the breaking, and the remaking of all the important polymers. So, we recognize that the different waste streams have different technical pathways. So through Green Circle, we've built a portfolio of technologies that so far includes 2 mixed waste plastics recycling technologies. One is a large-scale plastics pyrolysis. This is really kind of a centralized approach to chemical recycling. So bring a bunch of plastic into one location, kind of 20 KTA and above is how we look at it. Perhaps directly integrated with those downstream petrochemical assets. And then the other is a small-scale distributed modular microwave-based system. And the idea there is kind of the opposite. It's to decentralize and distribute the chemical recycling units and kind of put it closer to where the plastic waste is generated. We also have a PMMA depolymerization technology. So PMMA is acrylic or plexiglass. And this technology takes that material and depolymerizes it back to the MMA monomer, which can then be sent on to be repolymerized back into PMMA or sent to the other many uses of the MMA monomer, like adhesives and coatings and paints and whatnot. We have a tire pyrolysis technology. So this takes end-of-life tires and converts it into also pyrolysis oil and gas, but importantly in this case also a recovered carbon black material. It's a very valuable material that can complement virgin carbon black and in use in all sorts of different rubber applications. And then finally, we have a technology that produces a biodegradable polymer called PHA, or polyhydroxyalkanoate. This takes vegetable-based feedstocks like soybean oil and canola oil, palm oil, used cooking oil, converts it into PHA, which is a very versatile polymer. It's naturally occurring and biodegradable in landfill and marine conditions. And so the idea there is to not recycle material, but rather replace virgin polymers from the outset with a biodegradable material. So, all these technologies obviously have different feedstocks and they produce different products, but what connects them all is the common objective of keeping that carbon in play and extending the value, the use of that material. So, in some cases that means converting the waste materials into products that can be converted downstream or monomers that can be recovered, and in some cases it means replacing those virgin polymers with bio-based and biodegradable feedstocks. A key part of our approach is also industrial fit. So we view circularity as an industrial systems challenge, not just a single technology challenge. That means that we don't separate it from the petrochemical industry. We think that it's something that has to integrate back into and connect with the petrochemical industry. So that's why our technologies are designed to work with existing assets like steam crackers and FCCs and hydrotreaters and hydrocrackers. So I guess to summarize it, I'd say Lummus's role is to move circularity from concept to industrial reality by combining feedstock appropriate technologies with downstream integration, and also the scale-up discipline to create practical solutions that are both credible and deployable.
Fantastic. And I think it's important to note that there are so many approaches, much like the complexity of creating our materials, the decomposition and the reverse processes are many as well. And it's not just one size fits all. Pyrolysis, depolymerization, gasification, all these technologies are just emerging and at various points in the cost curve at this point. So it's a great you're kind of taking all of the above a strategy there in doing so. I think that's a very healthy and smart approach. Maybe if I could say with you, Kyle, just on the bottlenecks, like when you're looking at that, where are the biggest bottlenecks that you're finding? Is it the feedstock preparation, the process compatibility, downstream processing? Where are or maybe there are many, so maybe you could just describe a couple of those. Thanks.
Yeah, I'd say that the most immediate and system-wide bottleneck is definitely in the feedstock collection and preparation. The conversion technologies are advancing, but the bigger challenge is getting a consistent specification-ready feedstock from those inherently variable waste streams. That inconsistency, that variability carries through the system. It can affect reactor performance, operating stability, product quality, and ultimately how comfortable those existing assets are with taking those materials into their assets. Process compatibility is absolutely important, but I think in many ways it starts upstream with feed quality. We spend a lot of time thinking about how to engineer around that variability in order to protect that downstream asset integrity. So in plastics pyrolysis, for example, that means that we place a strong emphasis on processing steps that address chloride management, metals impurities, moisture control, product quality, or product separation, so that the pyrolysis oil is produced in such a way that those downstream assets are comfortable accepting them as a feedstock. So, if I had to prioritize the bottlenecks, I guess I would say that feedstock prep comes first, process compatibility comes second, and then downstream upgrading comes third. And make no mistake, that downstream upgrading is very important, but I think it becomes much more manageable when the work upstream is done well.
That's interesting. And I think, there are other industries that have a much more straightforward challenge in recycling, is steel, aluminum, others. But I think that as the years have gone by, they've started to anticipate the recycling or the end of life into their design processes a bit, and so maybe make some decisions about what might go into what additives are used and so on to think not just of the useful life, but that end of life as well. And speaking of that, Seval, from Clariant's perspective, how do you support the plastics recycling industry as it exists now? How do you communicate with them and engage with them?
Yeah. So I would say it starts with we have asked ourselves what do we need to to be successful in this transition. What does the circularity industry needs to be successful here? And we think that we need fully integrated solutions. I mean, Clariant is a specialty company, specialty chemicals company, so we are material suppliers, and we do not see our role as enablers alone. We see that we need to fulfill the solutions to make them adaptable to the current situations, to the customer needs and requirements. So for this, we have developed what we call a multi-stage product portfolio, where, for example, in the chemical recycling, we have developed solution for the pyrolysis itself, for the technology, where starting from mixed plastic waste, you are producing the main product, pyrolysis oil. And depending on what the requirements of our customers are, for example, if they need to reduce the energy demand, since you probably know that the pyrolysis is a highly energy demanding process, or for example, pyrolysis, it's not really a selective reaction, it's hydrocracking, cracking, not hydrocracking. So that means maybe to have sort of control of the product distribution during the reaction, or even decontamination during the pyrolysis step. So this is the kind of technologies that we have developed to adapt to their exact needs and requirements for the pyrolysis. Then the main product, the pyrolysis oil, has normally to be decontaminated, to be treated before going to downstream processes. And here we have, I would say, developed on one hand simple technology where for cases where the customer only needs, for example, to make the oil stable for storage and transport, up to the other extreme where you have, I would say, technically more demanding process, so combination of treatment with hydrogenation, leading to very, very high quality bio oil, with the result that we have I would say a hydrocarbon mixture which is not differentiable from fossil source base, so that the result is that you can use it in the downstream processing, in the steam cracker, as really a feedstock not distinguishable from fossil source, so that you produce again olefins, polymers, and you really close the loop plastic to plastic. So in a nutshell, this is how on our side, we support the customers with the technologies and with a focus of being really adaptable to the real needs and requirements. Yeah.
Very interesting. Yeah, there's a lot of work to do across the organization, procurement, setting specifications, and so on. But let's dive into the engineering. I know we've got a crowd here that's really interested in how do we do this at scale from an engineering perspective. So maybe Kyle, just what does that system look like from an engineering perspective, and maybe where might the weak spots be in our technical readiness in that full cycle?
Yeah, I think from an engineering perspective, a truly circular system is not just one technology. It's a coordinated chain, like you were saying. So it has to connect collection, pre-processing, conversion, upgrading, product certification, and ultimately in-market acceptance in a way that preserves as much value as possible from each individual waste stream. So I think in that kind of system, the right pathway is chosen intentionally. Some materials are best handled through mechanical recycling. If you can mechanically recycle something, you should. But others can't be, and so chemical recycling is the right answer, whether that's pyrolysis or depolymerization. And then in other cases, neither of those things are going to work, and the best solution is avoidance. And so that's where replacing those traditional virgin-based materials with biodegradable or bio-based polymers might be the right answer. So I think the point is not to force every material stream through one solution. It's to route each stream to the pathway where it can deliver the most value and outcome, or best outcome. As far as the technical gaps, I think feedstock consistency, like we talked about, is one. We still don't have enough standardization in the waste streams that are coming in. Contaminant control, because those downstream specifications are stringent, so we need to be cognizant of those contaminants and develop solutions to deal with those and address them before going into those assets. And then ultimately overall chain integration, those interfaces between collection and conversion and upgrading and in market use need to be better connected. So to me, a truly circular system is one that is feedstock aware, It's pathway specific. It's compatible with existing infrastructure, and ultimately it's connected end to end.
That sounds easy.
Yeah, indeed.
No, I think that's the challenge, and the elegance of some of the solutions that have actually come to market is breathtaking. I think you mentioned the contaminants and some of the other. We sit in Washington, and we're trying to set create the policy space to allow for these technologies to go forward. I think what we often hear is the antagonist will say, well, there's it's not just a plastic. You're perpetuating these other things, the additives and so on, and they try to perpetuate the mystery of these ingredients. And I think that going back to the basics and showing how the engineering actually does pull all these things apart, and you have a very clear and pure outcome from that is something, a communications challenge that we still need to maintain. There are unfortunately those that wish this does not to succeed or proceed as quickly as we could in this, and that's something that we have to look at as well. Seval, I don't know if you had any ideas on that same question.
I will fully agree first with Kyle in terms that chemical recycling is a great example for this engineering perspective, truly circular economy, because as you said, you are starting with plastic waste, then through pyrolysis you produce pyrolysis oil, and after, depending on the contaminants, after decontamination level and saturation, you really achieve a feedstock which is absolutely not distinguishable from fossil source base. So that means here that's really a great example how you really close the loop, polymer to polymer or plastic to plastic. And it differentiates from mechanical recycling, for example, because you do not degrade the plastic, so that at the end it can really goes back to any type of application, which is not the case with mechanical recycling. By mechanically recycling, you always have a certain degradation of a polymer. You can use it only for certain type of polymers. It's not applicable for all type of polymers, and so that at the end, it's. So don't misunderstand me. It's a great technology. It's a great tool. It's not a competition to mechanical recycling, but it has its limitation. You need pure monostreams, for example, for mechanical recycling. Here with chemical recycling, you are using broader range of feedstocks. And at the end, you cannot recycle endlessly mechanically. And that's exactly what you address while using chemical recycling. That's why it's really, really important, because it's a complementary solution, and not a competition. So,
very much, yeah. I think if you look at even a consumer product like breakfast cereal, it's moving from a box with a wax pouch to a standalone multi-material pouch. Terrific innovation for decreasing the load size and the weight and so on and distribution, but it does introduce a very highly complex, multi-layered packaging that needs a new approach to recycling. So I think that we've moved forward in one important degree, but that gives us a new challenge to face with new technologies like this. So excellent ideas there. Kyle, going back to you. I've seen in your Lummus solutions, there's kind of a large scale and then kind of a smaller scale solution. So can you describe that a little bit and how those are deployed and how they might fit into the kind of the economy a little bit?
Yeah, so the large scale technology in that case, where it's a centralized approach, a centralized model. So again, the idea is to gather as much plastic waste as you can in one location, potentially, integrate it directly downstream with those existing assets and pyrolyze a large quantity of material all at once. The other side of that is the small-scale distributed model, and the idea there is to kind of in a very repeatable manner be able to quickly deploy small-scale units, so 5-10 ton a day kind of capacities, closer to where the plastic waste is generated. Oftentimes, part of the problem in the centralized model is collecting that much plastic waste and getting it all into one location. You're shipping a lot of air around when you're transporting plastic. So a part of the idea with the decentralized approach is to kind of densify that plastic waste into a liquid pyrolysis oil that's much more easily transportable to a centralized location for upgrading.
I think there's a fascinating trend, and we heard it on the energy as well, of the smaller modular nuclear devices and others that would be deployed where and when necessary. I think we also, frankly, in DC, the issue of permitting is also a big challenge. So the larger infrastructure sites are much longer development scale than you can do with the smaller ones too. So I think it's fascinating to see maybe a complementary energy and kind of end-of-life solutions being modularized and made available to municipalities and others as well as those in industry. So really, this is unlocking a very interesting scale. Maybe one more, Kyle, on the circular technologies have moved beyond. Some of them have not moved beyond the pilot phase. What are the key determinants for a technology to successfully scale that you've seen so far?
Yeah, I think the technologies at scale are the ones that solve more than just the chemistry. So, a pilot can prove technical feasibility, but commercial deployment requires, reliable feedstock, operational robustness under real-world operating conditions, product quality that can meet the downstream requirements, and of course, a business case that can adapt to ever-evolving market conditions. Pilot units are never intended to be profitable, so it's critically important to evaluate how the capital and the operating costs are going to scale at the commercial stage when you're still in the pilot stage, so that you can design the process to be competitive once it's commercial. In circularity especially, I think one of the biggest reasons that technologies stall in the real world is that the real world feed is far messier than the feed that was used to prove the concept. So the question isn't just about whether the conversion works, it's about whether the full system can run consistently, safely, and repeatably while producing a market acceptable product. And again, to our earlier point, I think deployment model also matters. In most cases, scale comes from the large centralized units integrating into existing assets. But in other cases, it can come from small modular platforms that can be very easily replicated close to where the plastic waste is generated. So again, we're pursuing both models because we think the commercial scale is not always about building bigger. Sometimes it's about building repeatably. So for me, the technologies that reach commercial deployment are the ones that are robust, they're repeatable, and of course, bankable.
Very interesting. Yeah, that's the the challenge in jumping into an industry and adding a big disruptive change like this. You have to accommodate the legacy designs and try to work around some of the limitations that are presented by how we used to do things. And I think as this becomes more and more mainstream and there's more and more business value to gain from it, I think we may see some of that designing for circularity up front, where you start to think about, well, this is optimally going to go through three life cycles, and how do we make sure that the kind of the mix of additives and other things are suitable for that from the very beginning of innovation and design. So, Seval, I think more general, maybe pulling back the lens a little bit, what's your advice to someone who wants to support the transition to a circular plastics economy?
Very good question. I think there are many different ways to look at this. If you are an engineer, as you were mentioning, I would say it's really important from day one to design for circularity, design for sustainability, in terms of choice of materials, in terms of design optimization, in terms of emissions. Do we have alternative feedstocks? Do we have alternative ways to produce something? So really from day one, I think in R&D, it should be already a must to have this check mark. Do we have a better alternative in terms of sustainability? So really designing for sustainability. Then I would say, if you are a consumer, here we have an important role to play, because each decision that we take when we buy something, that's really, really impact the products that we find tomorrow on the shelf. So we have really this power to decide with everything that we buy today for sustainability or not. And we see this really happening. We see the change in the consumption behavior. Consumer asking proactively for sustainable products, or asking questions where it's coming from, how many miles did you fly to come here, or recycled content, etc. So we really see this behavior, and I think it's important to be aware of that. We have a direct impact on the products of tomorrow with what we choose today. And I would say on a higher level, maybe on a more systemic level, I will absolutely advocate for policy frameworks. This is really, really key here, in new innovating technologies, because we have a technology to do that. The technology readiness level are already quite high. So we have the tools to change the situation, but we need also this technology to be economically viable and competitive. They need to be competitive to the corresponding linear models. Otherwise, I mean, which company would invest so much money, undergo so high risk and not making money? Nobody. Yeah. So we need to support this. We need the policy framework around this, the incentives, the regulations to make this happen, to support the transition. Yeah.
It's so true.
It's a team play. I would say we all have our role to play, and yeah, but policy framework is really key here.
That's a great point. And again, I'll reflect on what's happening in Washington. As we know, there's a very different conversation about some sustainability topics in Washington, or there might not be a conversation, frankly, on some of those topics. But we have the administrator of the Environmental Protection Agency, Lee Zeldin, really going out and strongly advocating for advanced recycling. And I say he's seen it as a new area of U.S. manufacturing, of kind of bringing back some of the kind of the manufacturing ethos, and looking at this not as a not primarily as an environmental good, but as something that's good for society and good for the business cycle. So I think that there is, there definitely is a recognition of it, which is a change from some of the past suspicion and kind of arm's length approach we're seeing. But then again, it doesn't automatically flip a switch. It does require all those other sections of society to work as well. Maybe Kyle, going back to you, the kind of the big section of society that our industry looks at is our customers. Like, what are the brands asking for when you talk about circular materials? What's that conversation like these days?
Yeah, I think what the brand owners and the downstream customers are demanding is fairly clear. They want circular content, verified circular content, without compromising performance. They want materials that can help them meet recyclability and circularity commitments, but they still expect the same purity and consistency and processability that they get from the virgin-based systems. They also want certification and traceability, so that they can, reliably stand in front of their customers with their circular content claims. And then, of course, in the end, they want it to be cost competitive with the virgin-based system. So, the market for this is obviously still developing, but the premium that brand owners and ultimately customers are willing to pay for circular content is still a bit unclear. The fact of the matter is that converting used plastics into circular materials is more expensive than doing it via the traditional route. So some sort of premium, whether that's paid for by the customers ultimately, just through their commitment for cleaning up the environment, so to speak, or whether that's through government subsidies, some sort of premium is going to need to be there in order to make the economics work. And maybe that's just in the near term until some scale can be built and the flywheel can kind of kick into gear and let the industry stand on its own. As for technology development, I think it's that demand from the customers is shaping technology development in a pretty practical way. It's pushing the industry towards better input quality, stronger contaminant management, tighter upgrading, and more dependable supply so that those circular outputs can reliably meet the downstream specifications. And I think it's also pushing the conversation away from novelty and more towards execution. The market's not rewarding circularity, kind of in the abstract. It's rewarding solutions that can be certified, perform in real applications, and also be deployed at a meaningful commercial scale. So I think the signal from the market is make it circular, make it certifiable, make it perform, make it available at scale, and then make it cost competitive with the virgin-based routes.
Fascinating. And a follow-up, maybe you mentioned you're in a variety of markets and a variety of technologies, tires, bio-based, other things. Where do you see, if you can dive into a little bit of your portfolio, but where's the growth? Where's the most ambitious growth right now, and where do you think that might bootstrap some of the other categories that are seeing less growth?
Yeah, so if I had to pick one, I'd say that the chemical recycling and mixed plastic waste still has the most commercial momentum today. The reason for that is it combines the largest visible waste streams with the strong pressure from customers and then ultimately brand owners. And then obviously it also has a practical pathway back into existing petrochemical assets. from a Lummus standpoint, again, that's why we're pursuing both the large scale and the small scale pyrolysis. And the reason that we've kind of developed both of those two solutions is because the infrastructure for collecting plastic is different here in the U.S. than it is in Europe, than it is in India, than it is in Southeast Asia. So the global market needs more than one solution and deployment model in order to meet these circularity commitments. I would say probably the next most compelling is tire pyrolysis, in my opinion. In this case, you're not only making pyrolysis oil and gas, but also that recovered carbon black material, which is in very high demand. And then also importantly for tires, that collection infrastructure and pre-processing is both a little bit simpler and more well established. In this case, you're shredding tires, you're removing the steel, you're removing the nylon, and you're making a rubber crumb to then be pyrolyzed. That's already being done at large scale, really globally, and kind of the collection infrastructure for tires exists. So we're seeing a lot of momentum in the market there for tires as well. Specialty polymers like PMMA and biodegradable materials like PHA, those are both very important, but they're still a bit more targeted in terms of feedstock pull and end market use. So overall, summarize, mixed plastics chemical recycling has the most momentum, but I think the bigger picture is that there are multiple circular pathways that are starting to mature in parallel.
Yeah, as any market, there's going to be laggards and those that go advanced, and you have to leverage the profits from those first markets to bring up those behind us. So from an engineering perspective, we measure a lot. There's the ideal of the golden batch. Like what's the perfect configuration to get to a kind of a linear production process? How do we, once we have something that's terrific, how do we go back and mine the data? What went into that? How do we repeat that, and so on? Circular involves new metrics, and maybe Seval, you can say how do you measure success? What does success look like, and what are you measuring for a circular production process?
Well, I would say one fundamental metrics, and you have already mentioned it, it's probably the recycled content, because it has really, you see the impact on the society, on the consumption behavior, and I think it's a good fundamental metrics we can follow and track. Another one is probably the impact on the climate. That would be CO2 savings. Yeah, for example, in the chemical recycling space, here we have CO2 savings possible ranging from 50 up to 80%, depending on what you are comparing to, or which technology to fossil production. So I would say, CO2 savings, because you can really measure the climate impact. And at the end, the ultimate metrics that we could use is really the tonnage, or the volume of plastic that didn't went to landfill, or that we did not lose to the environment. Yeah. So I would say in a nutshell, for society, for consumption behavior, recycled content is a good one, climate, CO2 savings, and at the end, the material that we were capable to really use at the end. Yeah.
That's great. Yeah, there's corporate level metrics, but also the product level metrics. I think that's what people are looking at, the more and more details on the products, that nutrition label almost of how much carbon and so on.
So on the back of the products. And
exactly, we're getting there. Kyle, anything on the metrics from you?
Not terribly different than what Seval had to say. I don't think that we should measure circular progress with one single metric. I think it's a system outcome. So if you only optimize for one number, you can miss the bigger picture. But if I had to prioritize, I think I would focus on two things, very similar to what Seval said. It's recycling rate, so how much material is actually being collected and recycled, and then the carbon intensity. The primary goal of the circular economy is to reduce the amount of waste that's landfilled or incinerated or ends up improperly disposed of. So by creating these new value chains that can accept this waste material and also make money doing so, we're going to decrease the amount of material that's not being recycled. But then at the same time, we want to be cognizant of the environmental footprint and the carbon emissions. So that's why we don't view incineration as an ideal solution for this. And we think it's important that as you develop these technologies, that we're cognizant of the carbon emissions and ensure that the technologies still have an overall net positive impact to the environment from an emission standpoint.
Excellent. A couple more questions, and we are going to open for questions in a little bit. The engineers and how many ChemE engineers in the room? Just See that? So we've got people here that are doing heroic work to keep our American chemistry assets running optimally as they age, and as we look to revitalize manufacturing in the States. We still have lots of challenges in making sure that we maintain safe and effective facilities. In addition to those challenges, how do we and maybe Seval, you can say, how do we start, or have you seen good conversations between the sustainability folks trying to build new products in a new way, introducing potentially new risks into those systems? How do you interact with the engineers, and how does that collaboration work well?
Yeah. So I would say Brittany has already very nicely said this morning that collaboration along the value chain is key, is requested, is not an option anymore. Yeah, thank you. And that's really the case here. And I can say from our perspective, we all have our core expertise. And it's very, very important to collaborate in this field, especially in new innovating technologies, because, for example, we are working closely together with engineering companies. They know how to design technologies. They know how to optimize them. We know how to design the materials. So it's really key to have this strong collaboration along the value chain. So really recyclers together with brand owners, with technology providers, with off-takers, really. And I think key it's also to have this collaboration at early stage, so that we can really bring the core expertise of each companies to make this happen at the end. Really key to start early this collaboration along the value chain, I would say.
And even within a company, there's a chance for collaboration. The product designers need to understand the limits potentially of the current infrastructure.
Absolutely. Let me comment on this. Within our technologies that we have developed, for example, for chemical recycling, we are collaborating cross business unit with adsorbents business unit and catalyst business unit, where we have combined our expertise to come up with technologies which are adaptable to our customers. Yeah. Exactly.
Perfect.
Even within companies. Yeah.
That's great. Kyle, any hints on that as well? Just the aspirational thinkers in the business and the engineers to have to write the check for that. What do you experience there?
I mean, I agree completely with what Seval said. I think it's important to start early, make sustainability part of the design basis from the beginning. Just kind of as an example, and you touched on this earlier, but one of the things we deal with in plastics pyrolysis is how to deal with all the additives that are added to polymers for properties like heat resistance and color and strength. Things like chlorides and silica, nitrogen, arsenic. And these are all part of the feedstock that enters into the chemical recycling plant. So ultimately they're going to end up in the pyrolysis products, which can necessitate additional treating. So, if the different stakeholders in the industry can collaborate to explore how to achieve those same product properties by maybe using additives that are easier to process downstream, then we can improve the economics of the whole thing and increase the amount of recycled content. So, again, I think it's thinking to the end with sustainability in mind from the beginning of the design process.
Great comment. And I think it's just we have to reflect on how rapidly these polymer technologies have been introduced into society. We've solved so many problems. We've lightweighting, the miracles that have come with these innovations have been so rapid that sometimes we haven't caught up on the end of life thinking yet. But I mean, we're still very at the very beginning of this innovation cycle. But now it is time to do it responsibly. And in the American Chemistry Council, if I may say, we have a program called Responsible Care, which many of you may be familiar with. We've recently, many of the new advanced recyclers have joined ACC to undertake the Responsible Care program in their facilities, because they see the very same issues that you do. As this is not something that's just a cowboy culture, if I may, here down in Texas, where you just run and go as fast as you can. We have to do it safely. It's our obligation to society to do it safely. So in addition to innovating and finding solutions for everyone, we have to have zero error in our execution. So there's a lot riding on this for our industry. So given that, I'm going to kind of have one wrap-up question, then we can open the floor. Is 10 to 15 years into the future, Seval, what's the difference? What does it look like in 10 to 15 years with all of these technologies, if you can dream?
Oh, thank you. So if I can pick up one, I would absolutely say chemical advanced recycling, because it's it's really a complementary solution. That means we are not competing with existing and well-running technologies. That's the first point. Then it's using a feedstock which would not have been used otherwise. So it's not competing in terms of feedstock. It's producing a product which is really closing the loop, plastic to plastic. So you can use it in any applications at the end. Yeah, I would say that would be really what I wish to see in 15 years, the chemical recycling being established in that terms that at the end, then it would mean recycling is not a target anymore, but it would be our operating model. Yeah, that would be what I wish.
Yeah, bring it into the main KPIs of the organization. I love it. How about you, Kyle? Where do you see us in 10, 15 years?
Yeah, if I look ahead, I think the biggest accelerator would be system level standardization and integration more than kind of any single technical breakthrough. The industry already has many of the technical building blocks, but what we still need is that interoperability across the chain. You know, again, like we've talked about, from waste characterization to upgrading to certification and ultimately in market acceptance. I think the real unlock would be a system where feedstocks are better characterized, the right pathways selected for each material stream, upgrading is built into the design from the start, and certification and measurement frameworks are harmonized well enough that the market can trust and adopt these solutions. So, you know, I guess I'd summarize it by saying that the biggest breakthrough will be turning circularity from a set of promising projects into a coordinated operating model for the industry.
Fantastic. I think if we look at the energy extraction industry as a role model, it used to be you needed one big, you know, well, and you had a large pool of resources to pull up. There was a lot of gas and oil, you know, embedded in the rock, but there was no way to get at it. And fracking became a reality, and it allowed us to take the small, you know, elements of value and bring them together into something larger. I think that we're starting to see that same ethos here of, yes, it seems like, oh, it's scattered, the waste is all over, there's no proper collection way, but it just takes a few technology things and some policy and some collaboration, and suddenly you have a very, you know, kind of robust supply chain that you can then turn into something that's very economically viable. So great conversation so far. Lee, I wanted to open it up to the floor if there's any others that want to join us here.
Yeah, absolutely. So yeah, we'll open the floor to audience questions. Anyone have any questions?
Well, thank you for the discussion. It's very interesting, and I think it's a great idea to recycle the waste to produce fuel and other useful material. This is something like showing strong sustainability, and this is something one day we need to do. So we are the third-party lab to testing renewable feedstock and bio-based feedstock, and we know that sometimes there will be some challenges to testing this feedstock, but we kind of had a lot of experience to collaborating the experience to support our clients' operation. So my question is, because sometimes feedstock, like mentioned, there's contamination, there's need some metal testing, there's impurities. We have extensive experience on those. Then my question is, but in Houston, petroleum refinery is still the majority. Do you guys think in near future there will be more large-scale renewable projects?
Either of you care to take that?
Well, I certainly hope so. That's what we're out there trying to do. You know, I think like we've talked about up here, it's not just a technology challenge, but also needing, you know, the right policies in place to drive the market. But you know, I think everybody's working to do their part in their particular lanes, such that ultimately, yeah, that's the end result that we're aiming for.
Yeah, and coming back to your comment regarding the impurities and contaminants, and I can absolutely confirm that was the hardest part of his work, of establishing the proper analytics behind it. really, because the technical hurdle is here. I would not say really the contaminant profile itself, because that's something we can handle in the chemical industry since many years. Yeah, it's much more about the fluctuation of it. Yeah, you are handling waste, and as such, it's not homogeneous. It's not really specified. So depending on the technology that you use, depending on the region where the waste is collected, the sorting facility, even depending on the season. Yeah? In winter, we have a different waste than in summer. So you will have this heavy fluctuation. You have a large profile of contaminants, but much more of a hurdle behind is really this fluctuation. And to address this with a robust technology, but also with a proper analytics. Yeah, fully agree.
And I mean, we're sitting in Houston. You're asking about Houston. I mean, this area happens to have a very high functioning, kind of efficient way of doing it the legacy way. Many of our members in ACC who have facilities here and they have facilities in Europe and Asia are selecting other countries to do their first iterations of this, because there is, for example, there's no landfill in Europe, so that there's a very different kind of incentive there. So I think that, as we all know, you have to go through 4 or 5 iterations before you really kind of feel a sense of mastery on these things. And I think it's okay to start where the demand is and where the market is asking for it. It's not always as fast as you might want, but I think that we have to be practical. Indeed, there are some very exciting large-scale advanced recycling facilities that are now in production in Texas, and so I think we're starting to see that emerge. But again, it's much more right now. The innovation is, I think, happening in Europe and elsewhere. But these are transferable technologies, and I think we'll see that as it becomes more economically viable.
Fantastic talk. Thank you very much. I'm Gary Gildert from the University of Houston. One comment that I heard is that pyrolysis oil is still more expensive than fossil sources. So my question is, how can we close that gap? Is it advances in the processes? Is it more effective and lower cost contaminant removal? Or do we have to do something on the feedstocks and the policies? Or do we just tax fossils more to even this out?
I think you have already answered the question. So it's really all of those, exactly. Yeah. Because it's a bit unfair to compare it for established processes. They are optimized. I think you cannot optimize them a lot again. So, and here you are really at the very early stage of innovative and new technologies, and we have to support them with policy frameworks, with incentives, but also to optimize this process in terms of feedstock selections and all the way through the value chain. So yeah, it's all of those, I would say. Yeah.
All of the above.
Yeah.
I don't know if I was going to say the exact same thing.
How can you say all of the above in another way?
Exactly.
No, but I do think that, from looking at it from the policy side, and we saw a rash of tax incentives come and go under the Biden administration. We're seeing investment tax credits as a viable solution, even in this administration. And as I mentioned, the administrator of EPA sees this kind of the expansion of our manufacturing base being advanced recycling. I think we can probably make a case for tax credits on advanced recycling as a manufacturing technology. So we're going to be looking at that on behalf of our members to do anything possible to decrease the net cost of producing it, so that once it hits the market, it can compete. But again, it's only one part of the larger rubric here. Thank you for the question, though.
Excellent. So let's try to get one.
Hi. I would like to know, so you mentioned chemical recycling and mechanical recycling. So I would like to know what activities and developments you have in this solution. Because in Europe, for example, it's a big topic. And also I'd like to know on the textile recycling, if you have any developments, because also it's a big thing worldwide, but in Europe it's, so this solution and textile recycling. Thank you.
So let's start with the chemical recycling. We have developed all this multi-stage product portfolio where we adapt to the customer needs. So that means we have products for pyrolysis itself, as I was mentioning, depending on if you want to reduce the energy demand, if you want to somehow control the product selectivity, etc. Then along the decontamination part of a pyol, depending on how demanding you want to, or which quality you want to achieve at the end with pyol, we can adapt our process to I would say, low capex, low technology to just have pile stability so that you can use it further down, or to the other extreme to really have a high quality product so that it's really steam cracker compatible, so that you really close the loop. Yeah. In the textile industry, I would say we do not have any solutions there, but yeah, compared to mechanical recycling, what we can do is here to provide solutions. For example, when it comes to use recycled plastics, we have now a new, I would say, new issue coming from the recycled part of the plastic is VOC. For example, yeah, VOC removal and odor removal, because you see the trend in the market where, for example, automobile industry, they are pushing to increase the recycled content in the cars due to the heavy weight of a battery. You have to compensate this somehow, so they will go and replace more and more with recycled plastic. But this plastic has now the other challenge that it comes with VOCs and the odors from the contaminants. And here we have developed products to tackle this VOC and odor removals. And we are working closely together with OEMs in this field. Yeah.
Anything to add?
I'll just maybe touch on the textile recycling question a little bit. It's not something that we currently have in our portfolio. It is one of the gaps that we've identified there being a need for. So we're actively assessing and looking at various technologies to do that. There are quite a few players out there in industry that have developed technologies and that are working on getting them to scale. So not yet, I guess, is the answer from Lummus's perspective on textile recycling, but definitely identified as a need to fill some of the remaining gaps in the portfolio.
Well, I want to thank our panelists, Seval and Kyle. Can I have a hand for our experts here? This is great. It's a great conversation. I just think between the energy conversations and this, we are in the midst of a radical reinvention of what industry looks like globally, and we have an opportunity to really think that through here in the States. It's really exciting technology. I think it's going to take a lot of work to get us to kind of mainstream. But if you look at aluminum, you look at other materials, they might have had an easier road, but the cost benefit became so compelling that it started to become a virtuous cycle. And I think we just have to get to that point with the plastics and a few of these promising channels. But again, I want to thank the discussants here and really thank you for the great questions as well. Thank you.